The spaces described by a falling body from rest with a uniformly accelerated motion are to each other as the squares of the time intervals employed in traversing these distances. Galileo, Law of Falling Bodies. Now, this is a very dense statement, and this is from about 400 years ago. Galileo was studying the nature of acceleration, and this was especially hard back then. It's still hard because there's really no good way of measuring time back then. They didn't really have the precision we have with clocks and timers that we have today. And Galileo, he made a very shallow ramp and had a ball go down a very shallow ramp and measured the distances in one time interval to the next. It doesn't really matter what the time interval is. It could be 1 second or 5 seconds. It doesn't matter. But he measured how the distances change as an object rolled down a ramp, and he measured it in equal intervals. So much like what we did with the video analysis, we used the video to analyze the marble at very specific points as it's rolling down the ramp. Now, before we actually dive into the nature of acceleration, we're going to just back up and rewind and take a look at constant velocity again. So we have a car, and let's say the car is moving at a constant velocity. That is, it's just going the same amount of distance from 1 second to the next. So please pay attention to the position graph and the car at the same time. So you can see as the car is moving forward, every second it gains the same amount of position. And you can see the graph, right? It goes from 20 to 25, 25 to 30, 30 to 35, 35 to 40, and 40 to 45, right? In the first second, it went 5 meters. In the second, it went 5 meters, etc., 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 right? Every second, it goes 5 meters. So, since every second it goes 5 meters, the velocity is 5 meters per second, right? The slope is 5, and the units are meters per second. And if we graph the velocity, it's a straight line. The velocity never changes. So it's always 5 meters per second. So if you just graph 5, 5, 5, 5, 5, that's a flat line. Now, acceleration is how much the velocity changes from 1 second to the next. It's defined as this. It's the change in velocity over the change in time. Now, if you look at this line, the slope is 0, right? There's no change in velocity, right? It doesn't matter what point you pick. The change is always 0. So the rise is velocity. The run is time. So 0 meters per second per second. There is no acceleration here. So if you have a constant velocity, constant speed, you have no acceleration. The object is not speeding up, not slowing down. It's just staying at a constant rate, a constant speed or velocity. Okay. I always find it useful to look at it in table form because you can really kind of see the nature of the numbers in table form. So again, the car is moving at a constant velocity. Every second, it's gaining the same amount of position. So let's look at the velocity. If it's moving at a constant velocity, the velocity is 5, 5, 5, 5, 5, right? And since the velocity is always 5, the change in velocity is always 0 between any of these points that we look at. And now since the speed or velocity is 5 meters per second, every second it's gaining 5 meters. So 20, 25, 30, etc., etc. So it's gaining the same amount of position from 1 second to the next. There is no acceleration here, right? It's not speeding up, it's not slowing down. It's just moving at a constant rate. Now, because of that, the acceleration is 0, right? If you're moving at a constant velocity, the acceleration is 0. You're not slowing down, you're not speeding up, right? Look at this. It says 0 meters per second per second. Every second, the car is gaining 0 meters per second. So that's why it's always staying at 5. Now we're going to look at acceleration. Now, again, your car is dripping oil or transmission fluid. Now, let's say it's dripping oil every second. Now, because of that, as you're speeding up, those dots on the road, your drips of oil on the road are going to get further and further apart. So take a look at this data right here. So you can see how the graph is curving up because look at these positions: 0 meters, 2 meters, 8 meters, 18 meters, 32 meters. So you can see from as time is going on, we travel, in the first second, we only travel 2 meters. We're really not that far. In the next second, we travel 6 meters. in the next second, 10 meters in the next second, 14 meters, etc. That's why this graph is curving upwards. It's just curving more and more upwards. We're covering more and more distance, right? So the first velocity, these are the instantaneous velocities, right? The velocity at time 0 is 0. The velocity at 1 second is 4 meters per second. The velocity at 2 seconds is 8 meters per second. The velocity at 3 seconds is 12 meters per second. The velocity at 4 seconds is 16 meters per second. So these are the instantaneous velocities, the velocities at a very specific time. So you can see the velocity is always increasing. So when you're accelerating, so in this case, this is considered a positive acceleration because we are gaining velocity. But you got to be careful with the sign of acceleration in physics. It can be a little bit more obtuse. But for this basic example, this positive acceleration is causing the position to go further and further up. It's causing you to cover more and more and more distance. So the acceleration is 4 meters per second per second. Every second, you're gaining 4 meters per second. That's what acceleration is. It's the rate of change of velocity. Again, every second, you're gaining 4 meters per second. So that allows the car, so you can see it covers a greater and a greater and a greater and a greater distance from 1 second to the next. Again, let's see the animation. Now, since the acceleration is 4, every second is gaining 4 meters per second. So it goes from 0 to 4, then goes from 4 to 8, then 12. Every second, it's gaining that amount of velocity. So the change in velocity between every second is 4. So if it's changing by 4 meters per second every second, that's the acceleration. Acceleration, the rate of change of velocity. Now, position is a different story. Now, if you look at your lab data, you will start to see some patterns. Like, let's say at like the first time interval, let's consider the first time interval from 0 to 1. And let's say you're going from 0 to 2 meters. Well, if you double the original time interval, instead of 0 to 1, we look at 0 to 2, that's double. It's not going to double the position, it's going to quadruple it. So it goes from 2 to 8. And if we triple the original time interval, instead of 0 to 1, we look at 0 to 3, that is 9 times, etc., etc. Now, this still may be very curious to you, like how these numbers really came out of existence. Well, Galileo when he took data from this marble rolling down this ramp, and he noticed this pattern. He noticed that in the first second it would travel, say, for example, 2 meters, and in the next second it would travel 6 meters and 10 meters and 14, right? Every second it's traveling a greater and greater and greater distance, right? Because it's speeding up, right? Of course it's going to travel 18 meters because here it's moving fairly fast. It's moving 16 or 20 meters per second. So of course it travels a great distance in the last second. Now, the relationship that Galileo realized is acceleration follows the squares. So 2 meters, 1 squared times 2, 2 squared times 2, right? 2 squared is 4, 4 times 2 is 8, 3 squared is 9, 9 times 2 is 18, 4 squared is 16, 16 times 2 is, 32, and 5 squared, 5 seconds squared times 2 is 50, right? Galileo noticed this relationship. Now, we've got to be careful here. Now, this example is very specific. It starts from rest, and it starts from the origin, right? It's a little murkier. It's a little bit more obtuse when it's not from rest, and it's not from the origin. But when an object does start from rest, and does start from the origin, you notice this very distinct nature, right? The position follows the squares. So if we go back to the original definition, the space is described by a body falling from rest. It doesn't matter if it's falling or really rolling down a hill. The space is described by a body falling from rest with a uniformly accelerated motion are to each other as the squares of the time intervals employed. So you can see that he noticed this, right? The squares of the time. We don't say it in such a fancy way, but we're just saying that there is a relationship. The position increases with the square of time, and that's it. And we will be building on these concepts of acceleration.